compared to alpha. But for protection, see, I guess if you, as long as you have a lab coat, you don't be walking around naked where those data particles like go right through your skin. But then again, the alpha particle is blocked by your skin, so not that we should be walking around naked anyway. So would you rather be exposed to a substance, a radioactive substance with a long half-life or a short half-life?
Neither. It's longer than my life, so.
So what does the half-life tell you about the reaction rate? Faster for a long half-life or short half-life?
Short.
Yeah, so the reaction rate is faster for a short half-life. So that means that for a short half-life, would you be exposed to more radiation or less radiation in a certain period of time? Yeah, so for a short half-life, you'd be exposed to more radiation in a certain period of time than someone with a long half-life. So anyway, I guess really the choice is, given the choice, we wouldn't want to be exposed to any radiation. So that means, what about solar radiation? It used to be thought that having a nice tan was considered healthy. Is that a good idea? Yeah, probably not. Because I heard back in the Victorian days, whenever that was, it was actually healthy to have a lily white skin and never be exposed to the sun at all. It was considered really healthy. Because if you had a tan, that means that you were working, and who wanted to be working back then? Because if you were working, that means you were part of the labor force, and you weren't part of royalty, which meant that there was your position in life. And on the other hand, see, I learned when I was growing up that what's wrong with work? Work is good for you anyway. So that's all why we're all here to figure out what we want to do with our life in terms of working. Okay, so let's talk about nuclear fission. So uranium-238 is the isotope with the highest, which is the most abundant isotope of uranium. Now U-235 has an abundance of only 0.7%, and that's the isotope which undergoes induced fission. So note that induced fission is when U-235 collides with a neutron. That forms this metastable U-236, and this is actually one type of radioactive. This is one product of the U-235 nuclear bombardment reaction. So barium-141, krypton-92, some number of neutrons, gamma rays are produced, as well as 200 mega electron volts of energy. So how many neutrons are produced in this nuclear reaction? Okay, so to answer that question, what you want to do is write a balanced nuclear reaction and make sure that the sum of the mass numbers is the same on each side, and the sum of the atomic numbers is the same on each side. When you look at gamma, in the nuclear equation, gamma rays, they're not really a particle. Okay, so gamma this is the symbol for gamma.
For two is $20. I got two demo. So I think for a lot of people. Oh yeah.
Okay, so how many neutrons are produced?
Three.
Yes, it turns out that 3 neutrons produced. So anyway, when you add up 141 plus 92 plus, this has to be 3, that should equal 236. Okay, yeah, so it should be 3 neutrons. Now, in this reaction, note that 3 neutrons are produced, so what happens to these 3 neutrons which are produced?
Use the fusion again with the uranium-235.
Yeah, so that's going to collide with another U-235 nucleus, and this reaction will occur again. Okay, so note that because of these neutrons being produced, that's going to make this reaction continue. This is actually what's called the chain reaction. Okay, note that the energy released from the fission of U-235 is used to make electricity. Is also used in an atomic bomb, so that uranium-235 has to be enriched to 90%. So in other words, you have to go from 0.7% uranium-235 to over 90% uranium-235 to make an atomic bomb. That's not easy to do. Yeah, they have these specialized centrifuges to do that, things like that. Anyway, an atomic bomb undergoes uncontrollable chain reaction. So like you were saying, note that the neutrons which are produced will collide with U-235, and this reaction continues. So when it's uncontrolled, well, it continues. And anyway, we'll talk about how to control this reaction on the next slide. The first atomic bomb was equivalent to 20 kilotons of TNT. So let's take a look at question A. Calculate the energy from 20 kilotons of TNT. Now, how would you calculate the energy from 20 kilotons of TNT? This is actually a good review question. Okay, so TNT. What's TNT? Is it, let's see, Turner Network Television? Yeah, so TNT is, the T stands for tri, and then the N stands for nitro, and then the T stands for toluene. Yeah, so this is the structure of this compound. Okay, so this compound here is toluene. It has a benzene ring with that methyl group, and then for the nitro groups, you have 3 nitro groups here. So this is TNT. What's TNT used for anyway? Now we know that this is an explosive, so when it explodes, what do you think are the products of this reaction? Yeah, so when this reaction occurs, now this is a chemical reaction, not a nuclear reaction. So, Samson? CO2. Yeah, so CO2 is going to be one product. H2O. Yeah, water is going to be another product. Okay, so note that this compound has carbon, hydrogen, nitrogen, and oxygen. So we've accounted for the carbons, oxygens, and hydrogens. But what about a nitrogen product? Yeah? Yeah, N2. So nitrogen gas would be produced in N2. And there may be some other products. For example, maybe there's some carbon monoxide produced. What type of reaction is this? Yes, this is an exothermic reaction. Okay, so note that energy is also going to be produced. Now, how will we calculate the amount of energy produced in this reaction? Okay, so note that this equation isn't balanced, but to calculate the amount of energy produced in this reaction, you want, yeah, so you can use Hess's law. Okay, so to calculate that, use Hess's law. So we used Hess's law in Chem1A and also in Chem1B. So really, all we have to do is look up the heat of formation of each reactant product, and then apply Hess's law. Now I did this, and based on my calculation, I calculated that. Let's see here. I did the calculation. I actually did it for a ton. So I found that 1 ton of TNT, 1 ton of TNT releases, let's see, 4.18 times 10 to the 9th joules of energy. So how much energy is released from 20 kilotons of TNT? Okay, so to calculate the amount of energy released from 20 kilotons of TNT, okay, so that's going to release how much energy? Yeah, so note that a kiloton is 1,000 tons, so that's so 20 kilotons is 20,000 tons. Okay, so this is going to be 8.36 times 10 to the 13 joules, okay? Okay, so we know the energy produced from 20 kilotons of TNT. Okay, now before we go on, let's go to question B. What is meant by chain reaction?
It just keeps going.
Yeah, so once the reaction starts, it's going to keep on going. Now note that this is why, like I said, this is the function of these neutrons produced. So once these neutrons produce, this collide with another U-235 nucleus, this reaction continues. That's that chain reaction. What is critical mass?
The reaction goes from controllable to uncontrollable.
Yeah, so note that there has to be a certain number of U-235 nuclei for that chain reaction to continue. So once you get to that mass or that amount of U-235, that's that critical mass. So once the reaction starts, it's going to continue to go. Okay, so that's that critical mass. Okay, let's do this one. This is what you're all interested in, I know. Calculate the mass of U-235 that is equivalent to 20 kilotons of TNT. So we know the energy from 20 kilotons of TNT, 8.36 times 10 to the 13th joules. How will we figure out how much U-235 we need, which is equivalent to 8.36 times 10 to the 13th joules? Okay, so how do we do that calculation?
Use your equation.
Which equation? No, yeah, those equations refer to TNT. Now we want to know for this nuclear reaction. That's for heat, so that refers to the heat transfer. The heat transfer from one object to another object.
Whatever that is. Can you use like E equals MC squared or something like that?
Yeah, so that's what we want to do. So note that what we'd have to do, we'd have to look up how much mass is destroyed in this reaction. And like Omar said, once we know that mass, we can use the equation E equals MC squared to calculate the amount of energy produced in that nuclear reaction. Okay, so when we look up, okay, so for this reaction here, we want to figure out how much mass is destroyed. Once we figure that out, then we can use the equation E is equal to, I'll call it delta M times C squared. Now this equation here is going to give us the amount of energy released in that reaction. And note that the amount of energy released is actually equal to 200 mega electron volts. Okay, so it turns out that, let's see, an electron volt, okay, so the charge, when we're looking at electricity, we said that energy is equal to, what was the equation when we're looking at electrochemistry? How is energy related to charge and voltage? We said that energy is equal to
charge times voltage.
okay, charge times voltage. So note that